Welcome to the 8th lecture for Radiochemistry 702. This lecture is on accelerators and isotope production. This lecture will cover topics related to particle generation and accelerators, particularly different types of accelerators listed here. We'll also discuss cyclotrons, which are accelerators that are used to produce photons and some of the uses of these photons as spectroscopic tools. We'll also talk about heavy ion accelerators, and then finally this lecture will end evaluating neutron sources. This lecture couples with the previous lecture on nuclear reactions, where we talk about what's necessary for producing isotopes. This lecture really covers a little bit more detail about those products that are used to produce the particles used in the nuclear reactions. And as a reminder, we're going to basically cover two types of nuclear reactions, where we have a particle coming in forming a nucleus, a compound nucleus, or it could be a partial reaction nucleus. And then we'll also talk about the formation of fission products or fission or neutron capture products. The first accelerator we'll discuss is a direct voltage accelerator. This simply just uses an electric field to accelerate particles. They were used early in the 30s for protons. They have different components that are shown here, rectifiers and transformers. And fundamentally, what's done is that a voltage is applied, a charged particle is accelerated in a field towards that voltage. It goes from one potential to another, passes through this potential, and then hits a target, usually having enough energy to produce a nuclear reaction. These are still used as injectors for high energy accelerators and neutron sources, spallation neutron sources, and these are commercially available products. The Van de Graaff accelerator builds upon the direct voltage potential accelerator. This generally has higher potentials, therefore you can get higher acceleration, higher energies of particles. These were first built in the late 20s, and a positive sphere, as shown here, collects the charge basically from a static type charge, and the equilibrium between buildup and loss dictates the maximum charge one could have on the sphere. An ion source or a gun, electron gun, produces ions or electrons which are focused into an accelerating tube. This accelerating tube is shown here, is under vacuum, and it has sections which define the path. There can be accelerating electrodes within it, and a well-focused beam can be produced. There may be a need for a magnetic analyzer because the beam can have different ions of the same charge. As an example, with the hydrogen, dihydrogen, or trihydrogen are all accelerated in this system. Building upon the concept of the Van de Graaff is the tandem Van de Graaff, or sometimes just called the tandem accelerator. In this case, ions are produced. They're formed into negative ion charges before it enters the accelerator. The negative ion charges are accelerated towards a potential. They get stripped. The electrons are stripped. Becomes a positive ion, which is accelerated towards ground. As you can imagine, this can be coupled into a number of different stages where the positive ion gets made into a negative ion. The acceleration occurs again. Proton energies with a tandem accelerator can get upwards of 45 MeV. Further extension of the accelerator can be the linear accelerator. Basically, it's an extension of the same concept, where repeated accelerations are achieved through small potentials. As shown here, potentials increase. You can have a number of different sections, and energies can get extremely high compared to the Van de Graaffs and even tandem Van de Graaffs. Alternating voltages are used, and ions are accelerated at the gaps in the accelerator themselves. These were first made again in the late 20s, similar to the other systems, so a lot of work was going on at that point. The cavities can range in size, as shown here. Also, you can have different waves, one the traveling wave and a standing wave for the electromagnetic radiation. Electron accelerators are similar to these linear accelerators. They can be pulsed machines, and modern electron accelerators can go up to 20 GeV. And positron acceleration is also possible. These electron accelerator machines are used for a number of different experiments, including scattering, photonuclear reactions, radiation therapy, and they're also used as a source for synchrotron radiation, which we'll discuss a little later. A specific example of a linear accelerator shown here is a proton accelerator. They can accelerate protons or other positive ions with large velocities, and so therefore have high energies. They use a standing wave acceleration. Drift tubes are needed to have the acceleration occur between the tubes, so they increase in length. These can be very large machines. At Los Alamos, at the Los Alamos Neutron Science Center, they can accelerate protons up to 800 MeV. These protons are used as production tools for producing mesons, neutrons, and spallation products, including isotopes, and some of these isotopes do find their way into medical applications. HILAC is another example of a heavy ion linear accelerator. These were developed at Lawrence Berkeley Laboratories. The structure was similar to the tandem Van de Graaffs. They can accelerate heavy ions up to uranium, and they had energy ranges of 10 MeV per atomic mass unit, so something with like uranium with mass units on the order of 235, 238 can get extremely high energies, and these would use for experiments on understanding relativistic behavior of ions, information on nuclear structure, high energy collisions, and these were also used as injectors into other accelerators. Another concept for accelerators that was developed were cyclotrons. As opposed to having linear machines, as the name implied, cyclotrons were circular machines, as is shown here with the discoverers of the cyclotron, Lawrence and Livingston. Shown here with an example of a cyclotron at Berkeley. However, the first cyclotrons are small enough to be held in one's hand, and these accelerate ions by multiple accelerations within a potential. The ions travel in a spiral, as is shown in this path here, where they're injected into the center. These sections called Ds, which are shown here, are magnets that can be shifted back and forth to provide a potential which accelerates the ions. As the ions enter this path, as they gain in velocity, they move further out. Gaining in velocity means they gain in energy. When they reach the end of the path, they can be ejected, put into a beam, and that beam used for experiments. The equations that drive the behavior of the ions are shown here, and it's a function of mass, charge, velocity, magnetic field, radius. So one can change angular velocity, energy as a function of magnetic field primarily. Charge of the ions are generally fixed once they're introduced. The mass of the ion is fixed, and the radius is also fixed. Often you would have the cyclotrons themselves named after their radius. So with these fixed frequency cyclotrons, you can accelerate acceleration can be chosen by a charge to mass ratio. Different energies, since this is dependent on the mass. You can also have sector focused cyclotrons, which are useful for heavier ions, and they create hills and valleys within the regions. Cyclotrons can also be used, as we saw for some of the linear accelerators, as injectors into linear accelerators for higher energies. Conversely, Linacs can be used as injectors into cyclotrons. Overall, one can get an evaluation of energy as a function of accelerator type and the year in which these accelerators were developed. You see, for work with nuclear reactions, this region, many tens or hundreds of MeV would be sufficient for producing nuclear reactions. So within this regime, currently cyclotrons are used for looking at subatomic physics, so energies become much, much larger. Accelerators, particularly electron accelerators, are used to produce high-intensity beams of photons that are used for experiments, and within our program they're used to determine speciation and coordination chemistry of compounds, particularly the actinides and technetium. Under conditions where electrons are relativistic, they can produce continuous electromagnetic radiation when these electrons are curved in a magnetic field. This is due to relativistic velocity changes that are observed due to the Doppler effect. This is described through the Lorentz factor, where time contraction can also be described by this same Lorentz factor term. It produces a very intense forward-directing beam of radiation that is experimentally used. This is the equation that's used to describe the Lorentz factor, and as you can see from this term here, that it's only relevant at relativistic speeds, so one needs rather large accelerator systems for this. We'll describe two experimental methods, EXAFS and XANES, which are used from these photon sources. Overview of a setup for performing XAFS spectroscopy is shown here. Here we have a linear accelerator for an electron, which is then put into a booster synchrotron ring, then goes into an injector, gets accelerated into this storage ring. Number of synchrotron facilities keep the electron intensity or the electron number within the storage ring high. As the electrons bend, they produce this forward directed photons, which are then collected into beamlines, focused, and used for experiments. Here's another picture of electrons traveling in high velocity or relativistic electrons producing this synchrotron light, which then gets filtered. And then fundamentally you can take this light, treat it like you would other light, although it's traveling at energies that are useful for their X-ray type energies. But you put it in a monochromator, so it looks a lot like UV visible experiment. For example, you would have light coming in, hitting a sample, and then you can detect how much light passes through the sample. You can detect absorption. You can have a solid state detector here detecting fluorescence. And what would happen, what we're measuring is the absorption of this energy by this electron, and the electron is removed. We have the photoelectron effect. So by tuning, basically what one can do is tune what is the energy right here for, in this case, the K shell. For the actinides, we tend to look at the L shell electrons. Following on that concept of a simple UV visible experiment, one can perform XANES and EXAFS spectroscopy at synchrotron light sources. So imagine you had the sample that you were interested in, that light source. You had a light source which had variation in energy. We looked at the absorption energy edges, anywhere from 10 keV to the low 20s keV. The first absorption edge gives us information we call XANES, and then the extended area is the EXAFS. The XANES area is the X-ray absorption near edge spectroscopy. It starts at the absorption edge to about 40 eV above the edge. And the absolute position of this absorption edge tells you something about the oxidation state of the compound. So for instance, if we're looking at uranium compounds, where this edge is located tells us something about the oxidation state of the uranium. We can also get information about, if there's a pre-edge, about the symmetry of the molecule, and something about electron configuration. above 40 electron volts above this absorption edge, we start hitting the EXAFS region, which is the extended X-ray absorption fine structure region. Above this region, we get photoelectrons created by absorption of the X-rays. These photoelectrons, they can be backscattered from the X-ray absorption. We get oscillations above this edge. There's an equation. Here's the oscillations. Here's the number of terms. What's interesting about this term is that we can determine something about the number of coordinating atoms and the radius from the metal center to those coordinating atoms. So in other words, you can get information about the structure, the geometry, and the distance between the metal center and the ligands that are near that metal center. Here's an example of some EXAFS of bacteria. We see that this is this oscillation function, this K space, and what this is looking at the absorption of 22 millimole uranium and 4 millimole uranium on bacterial surfaces. And what we see we can take this and convert this through that equation into information that's related to structure, which gives us information about the distance between the uranium and the ligands or atoms on those ligands that are coordinating the uranium. You can get distances, in this case, on the order of 1.5 angstroms. This was generally known for UO2, 2+. So for uranyl, this is the uranium-oxygen distance. Then you can get information about other near neighbor shells, distances away, and the number of atoms that are coordinating. And we see from this data there are differences between the 22 millimole and the 4 millimole uranium sorbent on the bacteria surfaces. Here's the full data analysis from this work was used to show that there's this axial and equatorial oxygen. So the axial is from the uranyl, the equatorial are the oxygen atoms that coordinate to the equatorial environment of the uranium. And one can also look at uranium, oxygen, phosphorus. So this gives an idea that uranyl phosphate, both monodentate and bidentate, binding the uranium on the bacteria. In the 22 millimole sample, we see very similar data, but we see a mixture of phosphate and acetate structures. Some other structures are thrown in. The acetate becomes important because we saturated the phosphate structures, unlike the previous slide, where those phosphate structures were dominant in the coordination of the available uranium. We're going to end this lecture with a discussion on neutron sources. Primarily, we'll focus on fission, so we'll have a description of fission following this, since reactors are the main source of neutrons. However, there are other neutron sources which are available. Californium-252 has a relatively large fission, spontaneous fission branch, which can be used as a neutron source. There are also accelerators, deuterium-based accelerators, tritium-deuterium-based accelerators, which can also produce neutrons. We can also have gamma-N reactions, such as gamma on deuterium or beryllium-9. There are also neutron sources where one produces the neutron by having an alpha particle on a light element. So beryllium sources with alpha emitters, so plutonium beryllium sources. And then finally, there are a number of reactor. We'll discuss fission. And then we'll also discuss spallation sources, which are examples of using protons to produce basically induced fission in compounds or elements that you wouldn't think would normally fission. And an example that we'll talk about with this is showing how high-energy protons can split thorium-232. In the fission process, the fission products of the isotopes that we're most familiar with, uranium and plutonium, undergo an asymmetric mass distribution. And that asymmetric mass distribution is shown here. And this is for uranium-233, uranium-235 in red, and then plutonium-239 in blue. We see that there's a high peak, which is consistent. That mass doesn't tend to change for the different isotopes. This lower peak, we see that the peak increases with A. We have a mass distribution ratio of high to low of about 1.4 for uranium and plutonium. And these peaks, as we've discussed earlier, they're due to shell effects from the magic numbers. The peak is close to 132, which is a doubly magic 50 proton, 82 neutron, so that'd be tin 132. Symmetric fission is suppressed by a couple orders of magnitude relative to asymmetric fission, and this is all due to shell effects. In nuclear reactions, this can also occur, and the fission will compete with evaporation of nucleons in the region of high atomic numbers. So in other words, if you make an isotope from a nuclear reaction, it can undergo fission once it's formed as opposed to de-excitation by, for instance, emitting neutrons. We'll discuss this a little bit more when we talk about nuclear reactions. So as we've seen, the location of the heavy peak pretty much remains constant for the uranium isotopes and the plutonium-239. We see the lighter peak increasing. We can also see an influence of neutron energy, as what's seen here. This is for the 235 uranium fission yield with difference between thermal neutrons and 14 MeV neutrons. The obvious change is that as we increase the energy, this middle section, the yield, goes up. What we're seeing is that we're kind of washing out some of the shell effects with higher energy. As we've already seen for uranium-233, uranium-235, and plutonium-239, the fission yield distribution actually varies with the fissile isotope. With the previous isotopes we mentioned, the uranium and plutonium isotopes, that fission yield distribution was rather small. But we can imagine, as what's shown here, as I start to increase the mass of the fissioning nucleus, the heavy curve remains constant and the light continues to increase. We can imagine eventually that, particularly if we get at a close where Z is equal to 50, so Z being equal, where Z would be equal to 100, so that the fissioning isotopes would have a Z of 50, which is here. Fermium's a Z of 100. We can imagine that here we'd start getting symmetric fission. So if we look at fermium, as the mass of this fissioning system increases, the location of the heavy fission peak will start to coalesce with the light fission peak, and we can see areas on this curve where we're plotting N, the number of neutrons, against the mass of the fission fragments for the different, Z is plotted here. These are the different isotopes. We can see that those in the circles here are all symmetric. So we can definitely understand that the fission distribution is actually a function of, we've already shown it's the energy, but also the fissile isotope that's undergoing fission. Another aspect of fission products is how they are distributed. We've already talked about the yields being different, but even within a yield for a given isobar, for instance here the data is for A of 141, we have yields that can be either for specific isotopes, those are the independent fission yields, or the data that we see in the chart of the nuclides, the cumulative fission yields. For the most part, we've been working with the cumulative fission yields, which is an integration of all the independent fission yields for a given isobar. As we can see, the independent yields need to be determined for specific nuclides. These can be difficult to determine, especially with radionuclides fission products that are relatively short-lived. The data for both the independent and cumulative fission yields can be found at this web page listed here. You can find that you'll see that there's actually a relatively smaller amount of independent fission yields available. So the difference between the independent fission yields are shown here, where you have the dots on the line, and the cumulative fission yield is just the integration. And the cumulative fission yield, those are the data points that are available to us in the chart of the nuclides. We've previously described the distribution of fission products as a function of isotope. Now let's evaluate what actually happens with the nucleus as fissioning occurs. This is shown at the bottom of the figure, where the nucleus undergoes a change and eventually reaches a point where it's no longer stable. Imagine if we have charges, protons build up into the semicircular aspects of this nucleus. That charge eventually overcomes the adhesion due to nucleon-nucleon interactions. This is called the saddle point. And the rate of change of Coulomb energy is equal to the rate of change of nuclear surface energy at this point. And this induces that instability which drives the breakup of the nucleus. Beyond this point, we have fission. We have the scission point, where the nucleus divides into two fragments. The high charge in each fragment accelerates the particles away from each other, and we get about 90% of the final kinetic energy within a very short period of time, 10 to the minus 21 seconds. A final example of fission has to do with that's induced by other particles besides a neutron. And here we have an example of proton-induced fission. We see a fission mass distribution for the reaction of thorium with a proton. That produces this fission product, and here the fission product distribution for the reaction is a function of energy. And what we see is that the excitation, there's a definite influence on the fission product distribution with energy. As we see, we go from 13 MeV protons to 53 MeV protons. We start off at 13 with what looks like a typical two-humped fission distribution, as you would expect for something like thorium based upon the shell model. We're all the way at 53. We see that we get symmetric fission, which tells us that the ground state, lower energies, is really dictated by the shell model. And if we can overcome the shell model, we tend to see symmetric fission. And the amount of energy put into the system by the proton, 53 MeV, is enough to help overcome the shell model and allow symmetric fission product formation. We've covered different types of accelerators, particle accelerators, linear accelerators, starting off with the constant potential, going all the way up to high energy or heavy ion linear accelerators. Cyclotrons, where as opposed to having a straight line accelerator, one has a circular accelerator. Both these linear and cyclotrons accelerate particles. Then we talked about a specific example of synchrotrons, where the particle being accelerated is an electron, and we're interested, as opposed to the linear accelerator in the cyclotron, we're interested in the particles being used for nuclear reactions. Here we're interested in the light that comes off, and we gave an example of how one could use that for spectroscopic tools to determine something about speciation and coordination chemistry through XANES and EXAFS. And then we also discussed neutron sources and giving examples of fission and why some of the fundamental properties of fission, including the shell model and how it dictates the asymmetric fission distribution for fission products from uranium and plutonium. We also gave an example of what happens when you induce fission or have spontaneous fission from heavier elements, how symmetric distribution can be shown. Then we also provided an example of proton-induced fission, which is the source for spallation neutron sources. When you've completed this lecture, please comment on the blog and respond to the PDF quiz.